Okay. Let's start. Good evening, everyone, or morning, depends on where you are in the world right now. So the CDC 2023 Cooperative Aero Robot Inspection Challenge has concluded. And over the last 6 months, we've received registration and participation from like 20 teams all over the world, like 50% from China, and then we have like 3 or 4 teams from Europe, and then one participant from the US. So I consider this a success. So I hope you guys enjoyed the benchmark, and I hope that the choice of the um, bounding box is not that controversial, because I guess a lot of the participants, I believe I already stated clearly that the bounding box shouldn't be very detailed in the final scenario, and as promised, this is the choice for the bounding box of the MBS scenario. For example, as you can see here, originally we have Are you sharing? Okay, sorry. Share the screen. Okay. So you can see in in the original testing training scenario, we have kind of detailed bounding boxes covering the void deck here and then the three main buildings. I mean, so in the evaluation, I created one large bounding box that covers just the whole MBS, and then another one on the flower nearby that many people actually, I don't know whether you anticipated that this one would be um, considered for the inspection, and then another one in the tunnel area here, just a short area to see whether people have considered for the kind of non-convex area in their algorithm. So in the hangar scenario, the bounding box was chosen in three parts. So in the original, I had uh, uh, one bounding box along the fuselage and another bounding box on the wing. So in this one, I also do something similar, but this time the bounding boxes are not uh, going to be horizontal to the ground all the time. This one is basically just to take account of some kind of human error in this kind of deployment. We can't expect the operator in the field to have the perfect perception and knowledge of the environment to set like ideal bounding box. Okay, for the crane, the crane had the most elaborate set of bounding box in the evaluation in the training where I put myself 13 bounding boxes around these cranes. But eventually when we did the evaluation, I wanted to challenge everybody by just simply set 2 big bounding boxes here. So this means that in the challenge, in the evaluation, we actually had a lot of free space within the bounding box, and a lot of times I see that some of you just blew all the way out and then couldn't see anything from the border of the bounding box. So the result of this challenge is, as we have announced in the CDC evening, the winning team is Team Kios, Center of Excellence from University of Cyprus. Congratulations for your excellence. You made a great jump in the score from the first evaluation, which you submitted very early. And then after our feedback, you also fixed a little bit. And then for the second submission, you had a jump in the score, which is like congratulations for you. And then it's also a good strategy to submit early so that you can get the feedback, taking advantage of all of the program. And then the second team is Su Xin Hang from School of Triple E NTU. Congratulations for you. And at number 3 is team 313 Nonlinear Control Group from the number 3 is team Star from Sun Yat-sen University. So which one would we listen to their presentation first? There's also an XMU team, you rank number 4. So maybe we should go from the number 4 first. Is Bang Wei here or Ming Jie the one presenting? Yeah.
Here.
So okay, I leave the screen to you now.
Okay.
Can I start my presentation?
Yes.
Presentation. Hi everyone, I'm Mingjie Zhang from the STAR team. I'm here to present our algorithm strategy adopted in CERC. Allow me to introduce my teammates, Jinqi Jiang, Bo Yuzhou, and Fei Gao. Today, I will explain the algorithm strategy we exploit, which includes field and star searcher, developed by StarLab Let's start with the pipeline of our algorithm. Initially, the ground control station divides the UAV group into multiple teams, each consisting of an explorer and one or two inspectors. The GCIs then assigns the tasks to each team. Subsequently, each team independently completes their assigned inspection tasks without exchanging any information. They explore utilize data to acquire the point cloud information, while the inspector doesn't have this capability. They explore and the explorer maintain a voxel grid map and update it using sensor data, while the inspector can only obtain environment information from the explorer and update its own grid map accordingly. Our approach, our approach involves having the explorer rapidly explore the environment within the designed area and transmit the environment data to the inspector. At the same time, the inspector covers the surface of the target 3D scenes. Now, let's focus on our detailed algorithm, divided into 4 parts: task allocation, exploration strategy, inspection strategy, and trajectory planning. In the task allocation phase, due to the inspector's lack of environmental information, it remains stationary until the explorer approached and sends surrounding environmental information. This step, known as rescue, ensures the inspector can move safely to achieve optimal team allocation. We construct a graph where nodes represent boxes and edges represent real 3D connections. We model the task allocation problem as a CVRP and utilize the allocation algorithm to solve it. For box exploration, we mainly employ field. Although I will provide a high-level overview, I encourage those interested in field to refer to the paper and test the open source code. Field employs a frontier-based algorithm, defining frontiers as boundaries between known and unknown areas. Exploration of the entire area is accomplished through incremental coverage of these frontiers. Field divides frontiers into different clusters, generating viewpoints to cover each cluster. It then models an STSP and uses the allocation algorithm to find the optimal tour that visits all the viewpoints. Regarding surface coverage, we incorporate ideas from Star Searcher. Similar to Star Searcher, we modify the frontier definition, considering it as a boundary between free and occupied areas. Again, we employ the same clusters, clustering and viewpoint generation methods used in field and solved for an optimal tour. Finally, we utilize Fast Planner to generate smooth and collision-free trajectories for the controller to execute. It's important to note that we didn't employ any specific technique to address the light of sight communication problem. The only communication required is for inspector to receive maps from explorers. However, during the mission, we found frequent communication between team members. The messages received by the inspector can assist in planning a sufficiently long trajectory to account for the next communication interval. These are the results of our test in the example scenario, and we have achieved relative good scores. Thank you for your attention to our algorithm strategy in CARC.
Is there any question and answer part?
Can I ask how did you account for the in the interest bonds? Did you have any objective to capture the interest bonds with high quality, or it just inspecting the surface?
Yes, we use we inspect the surface instead of the specific interest points, and we found that it still works. It still performs good.
Any other question?
Hello. Here is Xinhao, and I want to ask you some questions. I noticed that you used something like the frontier first method, but I think in the bounding box situation that if you just use the frontier first algorithm, that you will search for a lot of the empty space actually, and don't care about the details on the building. Do you think maybe use some better, maybe there is some algorithm that can more suitable to this challenge and not the frontier first method?
Yeah, we noticed this too, and the problem you mentioned is really exists. The frontier will make the explorer to explore a lot of empty space in the bounding box. We found that if we use the surface frontier, it will perform much better than the frontier. The surface frontier is a subset of the frontier. It is defined as a free space, and its neighbor is both has its neighbor both has occupied and unknown. Then it will generate the frontier only near the surface, and we avoid to explore the empty space. The related work you can find in the paper of CMU Zhang Ji, Mr. Zhang Ji.
Okay, thanks.
Okay, can we, I think we have enough time, we have finished the time for one team. Can we move on to the XMU team? Hello.
Hello, Bangwei, are you there?
Okay,
You may
I'm
start.
here.
Yes.
Hi everyone, I'm Fang Weizhao from Xiamen University, and let me to introduce our rough method for the CRC problem. We okay. The first, the GCS will init the problem, and then explorers will construct a map and search points and send the messages to the photographers. And the photographers will process the interest points and navigate to take some photos and control the gimbal. We also need communication between them. First, we treat the the GCS will process the bounding boxes, and we get the face points and the inner points and send this message to all the UAVs. And then the explorer will construct a map and to a grid map and octo map. And the searching area will be the points in the bounding boxes and which is not obstacles like the blue ones in the below figure. And then he will set all the face points of the obstacles as potential detected points and send this message to the photographers. And his task is to explore as more as to explore the space to get as more as the potential detected points. We set a heuristic function to all the points, all the free space, the points of in the free space with with 4 parts. The first part is the distance to the UAV itself. The second part is the undetected points around there. Also, the distance and the flight height will be considered in. We first expand from the present position, and then we will consider some high score points far away from it. After get a series of explorable points, and we will rank them and use a stub algorithm to get a set of collision-free waypoints. Then we use minimal snap to get a trajectory like the green line shown below. Then we will check the trajectory. We will check that if the trajectory will have any collision with the obstacles. If there are any obstacles, we will check again to find a safe trajectory. We control the gimbal and the yaw of the UAV by our greedy method. We just face to the direction of the mass of center of the undetected points within a certain range. But we find that the UAV sometimes will face some direction we unexpected. As we has said before, the explorers will will get the initial map from the GCS position from other UAVs and send a grid map and to other UAVs. And the most important is that he should send the detect points and the interest points should be checked again to the photographers. For the photographer, they process the searching points from the explorers first. We use a two-fold cluster method. In the first fold, they will negotiate to allocate the points to 2 or 3 parts, and in each cluster, one photographer should explore all the points in it. And then in each cluster, we will cluster the interest points again to get a small batch of points, small batch of undetected interest points. And the photographers should travel through all the clusters. They will cluster again when they got sufficient undetected new points or after a certain time. In each small batch of undetected interest points, we will find visible points around it, and then we will find a path to connect all the waypoints by solving a TSP problem, and check if the path I check that if the path will collide with the obstacles. If there any obstacles, we will use a star to add some waypoints, and then the UAV will have no collision with the obstacles and go to the travel points. the gimbal, we control gimbal just towards to the next interest point, and this will not control, we did not control the gimbal together with the movement of the UAV, so the movement of the UAV will be easing strange. And as we said, in the communication of the UAVs are mainly map interest points and positions, and the collision avoidance here is mainly based on the path planning method. We get a collision-free path by far away from the obstacles and each other. That's all. Thank you for listening.
Hi, I want to know that how do you get the undetected interest points?
We just choose the base of the building as undetected interest points, and if we go around here, then we will set the detected and go to another position where the LiDAR has the information, but okay. In other words, the range of LiDAR is much more longer than the range we consider here.
Sorry. So you presume that if there is point cloud but no interest points, then it's an area that with undetected interest points. Is that right?
It's,
Okay, I got it. Thank you.
Hello.
Any other question?
Hello, may I know, because I may not catch this correctly, how does the explorer explore the unknown area?
saying, since as I just say, the LiDAR range will be much more longer than this range. So if we choose the undetected interest points here as detected, then there will be a lot of undetected interest points outside this range, and so the points with so the area far away with the UAV will get a higher heuristic function, and this drive the explorer to explore the space.
Okay, thank you. Okay, I think Tianming's mic has some problem, so we may go to the next speaker. So next speaker is Xu Xinhang.
Okay.
Share my slides. Okay,
Greetings, everyone. That here is Xu Xinhang, and I'm actually a research assistant in NTU Triple E. So please remember my face, and I'm glad to see you in the next CARC mission. So let's have a brief review of the whole task. Actually, the Kaggle mission is a multi-rule swarm inspection task based on rule prior knowledge of the target region. So we can just divide the Kaggle mission into the 4 parts that the group assignment, task assignment, exploration, and inspection. As for me, because I just designed a human experience, my design is just based on the human experience. So here are 5 questions of the explorer. That the first one is who is a follower, and the second one is which region is my task, and 3 and 4 is how to go to the region, and what should I do to the finish the exploration. And 5 is how can I lead the photographer to do the inspection scenes. And so based on the different ability of the explorer and the photographer, that we can, I just cited the desired specification of the group structure as at least there should be 1 explorer in the team. And I think if there be as many photographers as possible, that we can finish the task as far as possible. So based on the human experience, similar to the KNN, and at the group assignment part, the photographer will be assigned to the nearest explorer. And after the group assignment, and we need to tell which group should inspect which bounding box. So based on the human experience, special inspection along the longest axis of the bounding box may get more details. It's just my experience. So I just define this type of the exploration path. And so there are 2 another experience that if there are more drones participating in the task, the faster the task will be finished. And the second one is the fewer paths that are outside the mission area, the faster the task can be completed. So I have the solution of this task is, so for the global path or the global trajectory that we wanna is use the closest first routes to find a way via all the task regions, and I began from the team 1. Here I just use the closest first routes because I saw that the example, there are a lot of bounding box in some Korean example, I think. If I use the optimal solution to the such as the TSP problem, that may cost a lot of time. So I just use the closest first routes to do that. And but I found the global trajectory, we clip the regions based on the team size and assign them. So if we just follow these 2 solutions, we first get a trajectory from team 1, just go through the bounding box, go through the bounding box, go through the bounding box, and finish all the tasks. And based on the team size, we just assign these 2 bounding boxes to the team 1 and this bounding box to the team 2. So it's time to do the exploration and the inspection. And I base on the map. So this all the things should based on the map. So as I know that the large voxel map can deduce the calculation complexity when planning paths based on the searching method. And so I just converted the whole bounding box to this voxel map. And because the explorer is slower than the photographers because the size and the payload, and just assign the different regions to the photographers. Each region's factor is for explorer, photographer is 2 factors 3. So after assign all the things, that the explorer should know how to get into this task region. As the human experience, then the age of the layer 1, you can see the layer 1 or the layer 2, the age of the layer is more possible to be accessible free. This accessible free, that means I can use the A star, D star, or some search method to get a path to the bounding box. and I just select the closest edge voxel as the start point. If I can't find a way to this start point, I will search the other one, just as this sequence. If I can't find a start point in the first layer, and I will check the second layer, and so on. So also there is an experience that the photographers are blind actually, so it's best to have someone lead him. The photographer will follow the explorer on the way to the mission region. So that's ensured all the teammates and the team can get into their target task region. So after get into the bounding box, or you call it the task region, just fly around the building is enough to make a good map. So the explorer will first fly into the first layer and just fly around the building to build a map. After he finished the build the map, and he will call the photographers that there is the map and you need to inspect it. So how the photographer can inspect the whole things, that I just remember that we just built this kind of voxel map here. So the 6th neighbor voxel of the occupied voxel is actually my interest point. And I just want the photographer to visit all the interest point here. So that's all the things that I need to do. After they finish the exploration and the inspection, they will have a waypoint here, just like the some voxel just align with the flying point, and the explorer will wait here and the photographer will wait here. They will try to communicate with each other. If the explorer cannot communicate with the photographer, and it will fly around to search for the photographer. And once they communicate, they build the stable communication, and the photographer will follow the explorer to the next task region or fly to the home. So it's just I think it's a simple solution for this task, just based on the human experience, just some intuitive idea. So I just final got my final score is the 3.8K, and here is a video that can show my method. I just asked the organizer to have this video. So just say here, my method can light the explorer or photographer to fly into the curve to scan the inner space of the building. So it's not based on some convex optimization or some heavy calculation method. Is just based on my rules. So it's typical. It can run very fast, and there is no a lot of calculation here. And for the next this sense, I also got a lot of score here. I think I do the better in this sense because here is a deadlock in the Marina Bay sense. And also there's this sense is a problem that I just assume the any obstacle or building in the bounding box will have the interest point, so it will fly to the top of this sense and scan the top. And for the next, it also finished a good job, I think. So that's all of my sharing. Any question?
Okay. So in your method, you divide the teams based on the number of the drones, and then each drone has one explorer. Is that what you do?
Actually, so at the initial of the GCS or the whole task, I will record the initial position of the each drone, and all the drones know the other guy's position. So just assign the photographers to the nearest explorer, just like what in the K nearest neighborhood, this kind of clustering algorithm to assign the group. Yeah.
Okay, so you use the spiral trajectory to explore the bounding box. So how do you decide, say that what's the distance between each surrounding spiral? So it can be very dense or it can be quite sparse, right?
Yeah.
Chat. This is a very interesting problem because I just use some PSO search to get this distance, to get the optimal distance. I think we can just decide it based on the field of version, the FOV. But I'm too lazy. I just use some automatic way to find the optimal parameters.
Okay, thank you. So if there's no more question, then we will invite our last team to speak. That is Team Kills.
So you hear me?
Yes.
Okay. Hello everyone. I'm Angelos from GIO's Research and Innovation Center of Excellence at the University of Cyprus, and today I'm going to present the winning solution of the Comparative Area Rhombus Inspection Challenge. We will start with a brief introduction to the problem statement, followed by our proposed approach. Afterwards, we will present our highest evaluation score and we will close with conclusions. As you may already know, this challenge is about inspecting infrastructure using multi-UAV systems. It comprises three scenarios depicted in the figure below, where the infrastructure to be inspected is enclosed within specified bounding boxes. Scattered across the enclosed infrastructure are several points of interest that must be inspected. So the objective of the challenge is to inspect as many of these interest points as soon as possible. It's important to note that parts of the infrastructure may extend beyond these boundary boxes that should be considered as obstacles, making collision avoidance mandatory. In this slide, we provide an overview of our proposed approach. Our approach consists of three stages. Stage 0, which is responsible for the environment generation. Stage 1, which is responsible for mapping. And stage 2, which is responsible for inspection. Stage 0 takes place before takeoff. It starts with the GCS constructing a cuboid based on the initial position of the UAVs and the vertices of all given bounding boxes. The boundaries of the cuboid are determined using equation 1, which calculates the minimum and the maximum values of each axis. This results in the creation of the smallest cuboid containing both the infrastructure to be inspected and the UAV fleet. A visual representation of this cuboid is shown in figure 5. The last step in stage 0 is the construction of a discretized environment. This environment is formed by dividing the cuboid into voxels sized at 6 times 6 times 6 meters. The resulting 3D grid, shown in figure 6, is treated as a connected graph where each voxel represents a vertex. Subsequently, the GCS generates an adjacency matrix based on the 3D grid and transmits it to the UAV fleet. Stage 1 begins with the generation of points that are used during the mapping phase. The mapping points in figure 7 are generated in such a way that the explorers will traverse the long axis. The second step is in stage 1 is the construction of the occupancy map by each explorer in a distributed manner. As illustrated in figure 8, each explorer uses its LiDAR measurements to build an occupancy map across the previously mentioned 3D grid. This is done by finding the voxel that contains the 3D coordinate of the obstacle detected by the LiDAR and marking the specific voxel as occupied. Finally, upon completing the mapping process, the explorer merges their occupancy maps to create an initial map. Figure 9 depicts the presentation of this merged occupancy map. At the last stage, each UAV opportunistically exchanges and updates its occupancy map with every UAV that is in line of sight, as shown in figure 10. Using the updated occupancy map, each UAV generates waypoints around the occupied voxels within the bounding boxes. The representation of the generated waypoints is shown in figure 11. Following the waypoint generation, each UAV solves the multi-TSP problem with other UAVs that are in line of sight. Subsequently, employing receding horizon control, each UAV executes the generated trajectory. This entire process is repeated until the end of the mission time. In this slide, we present our best evaluation results. As you can see in figure 13, the proposed approach achieves a score of 1,870.625 in scenario 1, a score of 1,893.554 in scenario 2, and a score of 594.903 in scenario 3. Here we can see the proposed approach in action, inspecting the three infrastructure in fast forward. Conclusion, the effectiveness of the proposed architecture was validated through simulation using the multi-UAV benchmark for area robot inspection schemes, achieving the first place in the competition. So thank you for your attention.
Any questions from the audience?
Hello, I want to know that if you explore the whole scenes and then inspect the scene.
I can't hear you very well. Could you repeat your question?
Do you explore and inspect simultaneously or step by step?
No, we initially we map the environment and afterwards we inspect. So it's two stages
Thank you. I got it.
Can I ask, how do you solve the multi-TSP with the neighbor? Like each, can you go to the slide with the TSP result?
Yes, sir.
This one. So the UAV path and the UAV 2 path are solved simultaneously, right?
Yes, each UAV that. Yes. Sorry.
So is it solved by one UAV and then the
No, because both. Sorry, I will answer the question. Okay. Because both UAVs have are in line of sight, so they exchange information, and both UAVs have exactly the same information at hand. So both use the same algorithm to solve the TSP, so they end up with the same results.
Oh. Okay. Yeah. Thank you. I understand.
And each UAV given from you guys, each UAV already has an ID, so each drone knows which result to get from the TSP.
Yeah.
Any other questions? If not, I think that's all from our participants. And then in the end, I would also like to ask if there's any suggestions or any comments on the competition that we have organized, and any feedbacks from the audience or any from the participants. We would definitely want to bring this competition forward to the next iteration in other conference or other venues. So we will definitely welcome more feedbacks and more suggestions for improvements. Or any questions you may also ask at this time to our organizers. So maybe for one thing that one thing we learned from this competition is that the score that the teams get are not really a reflection of the coverage percentage of the actual coverage. So you may get like 20% of the full score, but that doesn't mean you only covered 20% of the area. In fact, we see many teams that have quite a good coverage, almost 100% coverage. So maybe in the future, we may consider a more comprehensive scoring metrics that may get the better scoring that reflects the overall coverage percentage. And in the current case, some of the points that we define the interest points are actually randomly scattered in the scene. So there are some interest points that are not totally reachable or not observable at all. So that is reason for the relatively low percentage of score that some teams get. So if there are other questions or other comments that you may have or you may think about in the later time, you may also will also welcome to send us emails or just drop us a message in the Discord chat. And we will hope to organize this again sometime later this year or the next year. And it also depends on our results in trying to apply for the competition session in other conferences as well. So any other things you want to add, Tianming?
On behalf of the organizers, and I would like to thank all of the participants for spending time on this challenge. We really learn a lot from your solutions, and we also learn how to organize this competition, and we will try to improve the procedure in the future. So I would also recommend you propose your solutions to the special issue of unmanned systems. All of the solutions and results of the challenges can be submitted to the special issue of unmanned systems. So again, thank you all for your participation in the Cooperative Aero Robot Inspection Challenge 2023. And we look forward to seeing you in the future. Thank you.
Thank you.
Can I ask the kiosk team whether you have received the monetary prize from the secretary?
Excuse me?
Can I ask if you have received the monetary prize from the secretary of the CDC?
I'm not the responsible person.
Okay.
I'll let you know by
Yes,
chatting
sure.
you. Yes.
Yeah.
Okay.
Because I remember
Okay.
Dr. Savas, we just handed him the certificate. I don't know whether the secretary provided the cash prize. Yeah. Thank you.
Okay.
Yeah.
Okay.
Okay. Goodbye, everyone.
Goodbye. Bye bye.
Bye bye.